In this project, we are going to simulate a flap effect on trailing edge of an airfoil. In this project, a steady airflow over a flapped airfoil with an attack angle equal to 12 degrees is investigated. Air velocity magnitude is equal to 45 meters per second. The lift force coefficient of an airfoil with and without the flap is equal to 1.2182 and 1.053 respectively, which shows the effectiveness of flap in aerodynamic lift force generation. Moreover, the drag coefficient of the airfoil in the presence of flap is equal to -0.0273, which is less than the airfoil without flap, where the drag coefficient is equal to -0.0822, which proves that the flap presence is effective in drag force reduction that is favorable in aerodynamics applications. The fluid domain's geometry is designed in the Design Modeler software, and the computational grid is generated using ANSYS meshing software. The mesh type is unstructured, and the element number is equal to 64,731. Now the first step for you to start the simulation is to click on a fluid flow block and then drag it over a blank space in ANSYS Workbench software. Next, right-click on Mesh and then go over Import Mesh File. Then click on Browse and then select the mesh file that is sent to you with the rest of the files. Now there are several assumptions taken into account for this project. First, the type of our solver is set to be pressure-based since we are dealing with incompressible flows. Second, we have selected absolute format for velocity formulation. And third, we have selected a steady time study since we didn't want our results to be a function of time. Also, since our model is in two-dimensional, we have selected planar 2D space. Now if you expand models and then double click on the viscous button, in the appeared window you can see we have selected the SSTK omega model to solve for our turbulent fluid equations. The SSTK omega turbulence model is a two-equation eddy viscosity model that is used for many aerodynamic applications. Also, if you pay attention to the options section, you can see we have enabled the production limiter option, since a disadvantage of standard two-equation turbulence models is the excessive generation of the turbulence energy in the vicinity of the stagnation points. In order to prevent such incident, this option is enabled. After double-clicking on the Boundary Conditions button, in the middle part of the software window, click on Inlet Boundary. After clicking on that, you can see the type of this boundary is defined as Velocity Inlet. By clicking on Edit button, you can change the settings related to this boundary. In the appeared window in front of the Velocity Specification method, change it to Components, and then enter the values for X velocity and Y velocity as you can see in this slide. By entering these components like this, the 12 degrees angle of attack will be taken into account for our airfoil. Now if you click on the outlet boundary, you can see the type of this boundary is defined as pressure outlet. Again, by clicking on Edit button, you can adjust the settings related to this boundary. The most important point you should pay attention to in this window is the gauge pressure, which has the value of 0 Pascal, meaning that our airflow will exit our computational domain to the atmosphere. And finally, if you click on each of the wall boundaries and then click on Edit button, in the appeared window you will see a stationary wall motion along with no slip shear condition are defined. After double-clicking on the method, you will see that a new window will appear showing you the pressure-velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first order upwind and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. After double-clicking on the Controls button, in the middle section of the software window, you can see that new part will appear. In the Appear part, you can see under Relaxation Factors for different parameters. Now, these values are set here by the software automatically. You can change these values, which are between 0 and 1, by yourself for different projects you do. But it is highly recommended that you do not do that, since it may result in divergence. There are two ways to check that your simulation process have reached convergence or not. Alongside checking the residuals reaching and nearing zero, you may define an arbitrary report or arbitrary boundary in order to calculate different parameters like pressure, velocity, temperature, and see whether they reach a constant value or not. If yes, it may be a sign that your simulation process have reached convergence. However, you must check the residuals as well. To create such report, you can simply right-click on Report Definitions, go over New, and select one of the options available based on your simulation. Now if you expand the Report Definition section, you will see different reports are defined. For example, if you click on the first report, you will see a mass flow rate calculation report is defined over the outlet boundary. As you can see here, under the report type, a mass flow rate report is defined over the surfaces of outlet boundary. The second report is a drag force calculation report, which calculates the drag force applied on the airfoil itself. And finally, if you double click on the lift report, you can see in the appeared window a lift force calculation report is defined over the surface of our airfoil. After double-clicking on the Residuals button, a new window will appear. In the Appear window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. After double-clicking on the Initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the Compute From drop-down list and clicking on one boundary. For example, by clicking on Compute From All Zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software. And finally, if you double click on the Run Calculations button, under the Parameters section, you have to enter the number of iterations you want your software simulation to be continued, and then by clicking on Calculate button, this process will start. Now in order to extract graphical contours, just expand the Graphics section, go over Contours, right click on it, and then select New. In this window, under the Contours of section, you can select your desired variable which you want to extract its contours. For example, in this slide you can see we have selected the pressure. And then by just clicking on Save or Display button, the software will show you the pressure distribution inside our computational domain. Now in this slide you can clearly see the pressure distribution inside our computational domain. Also, in order to extract another contour, you can simply change the contours of section, for example, from pressure to velocity. And then again, by just clicking on Save or Display button, the software will show you the new contour. And in this slide, you can see the velocity distribution of airflow inside our computational domain. Also, you can easily see the wake generated behind the surface of our airfoil due to the existence of an angle of attack for our airfoil. And now for the final contour, we're going to extract the turbulent viscosity contour for you. To do that, just click on Contours of section and then change it from velocity to turbulence. Then beneath the contours of section, Click on it and then select turbulent viscosity. And now, just like previous steps, just click on Save or Display button. And finally, in this slide, you can see the turbulent viscosity distribution inside our computational domain.
Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide. To benefit from Mr. CFD services, including simulation, consultation, and training, contact our experts via info@mrcfd.com.